do anything you want. Okay, so let's talk about local decodable codes, and I want to describe how local decodable codes connected to representation theory and maybe some ways to construct local decodable codes. Okay, so first of all, what local decodable code is? We have it's also the theme with in error correcting codes. We have some code which encodes our message f to the k to some f to the n. Okay, so this usual theme, and what usually we want from error correcting codes, we want to be able to decode. Once we encode it, we want to be able to decode our message even if it's corrupted. But in local decodable code, what you want to be able to decode even not only if when it's corrupted, but you want to decode only one symbol. So you want to do it efficiently. Okay, so usual theme, you have code and you encode your message C of m. You add here noise, and you have decoder such that it returns your message m. But in local decodable code, you want to have a decoder, and you don't really read all the message, but you get some symbol I, and you can access to the encoded message plus some noise, and I want that you will be able to return me some message mi, and efficiently as you can. And actually, what we count in local decodable codes, the number of queries, the number of access you make to the message plus noise. This is the usual theme of local decodable codes, and what we want to talk today is about local decodable codes with constant number of queries, say 3, and this is what we want to talk today. But the problem with this theme is if you make only 3 queries, then you have a bad guy, then he always can corrupt these 3 queries which we are want to query. So the theme here is that our decoding algorithm D is randomized. And he will make random queries, and so that the bad guy who adds a noise will not know this where we are going to query. Okay, so but I have to mention that today we are talking only about adversary noise. Okay, so our theme is the following: we have a message. We encode it to some long message. Now bad guy comes, corrupt some places. Now we want to be able to access few places and return mi. And what? Okay, so what the way usually you want to check that the code is locally decodable, you want to check 2 things. One is we'll have some decoder which makes only small number of queries to code word, and you want to check 2 things. It's soundness. That is that decoder with correct, uncorrupted code word, which receives uncorrupted code word and receives I, always returns mi with probability 1. And second, smoothness. And smoothness that each query of D is uniformly distributed Okay, so assume that we have these two soundness and smoothness. So we know that each query is uniformly distributed, say, over half of all possible places, and we have that if in case we get correct code word when we return correct answer, then I claim that these two conditions imply that our code is locally decodable. And why is it? Because assume that we have some code word, and no matter which if bad guy corrupts only small number of places, and we have that each of our queries is uniformly distributed over, say, half of a domain, then if he corrupts only delta fraction of places, then with probability at least 1 minus q delta, we will never see these corrupted places. And this why these two, and therefore it will be looked like we access uncorrupted code word. So actually, you don't need to remember what local decodable code is. These two things we are going to check today. Okay, do I need to motivate why people are interested in local decodable codes? Okay, so I will not. It's like very interesting in computer science, but I think today. So. Yes, it might. Okay, domain. All what I want is that for each I, and you have q queries. Each different query maybe have different domain, but with only two things. Not really. Oh, okay. So what's really important for you is that you will not have some small delta fraction of places where you have a high density, so that it will be. So because if you query some small data fraction of places with a high probability, then and bad guy comes and corrupt it, then it will be bad. Okay, so today we are going to talk about non-adaptive linear local decodable codes. Actually, I don't know about any local decodable code which have adaptive queries, and I don't know if this may help. So, but queries are here. They are non-adaptive, and okay. Okay, so what I want to say today is that almost what constructions of local decodable codes are known. First construction is based on read Muller codes. It's when you take multivariate polynomial of degree d and evaluate it on almost all points, and different variants on this code. This what gives you local decodable codes. And usually it's these constructions are local decodable codes, gives good construction for local decodable codes with many number of queries. And the second is matching vector codes. And this the framework which matches all sub-exponential known sub-exponential local decodable code constructions. And what we are going to show today is that both of these constructions could be constructed from representation theory, from the framework which we're going to show today. Okay? And okay, actually, I will going to show only the framework, not how these constructions fall in this framework. It's not trivial. Okay, so what else I want to mention is that there is a big gap in construction of local decodable codes between lower bounds and upper bounds. In case of for local decodable codes, the lower bounds are known only slightly more than linear. So we have something like n to the power of 1 plus epsilon, where epsilon depends on q. Lower bounds, and we have something like this upper bounds. And in fact, our understanding of local decodable codes is very weak, because it's one of the fields when where there was a lot of conjectures which appear to be false. So for example, it was conjectured for many years that local decodable codes should be, the constant number of queries should be exponential, and it was Johann found that it's possible to construct sub-exponential local decodable codes, and it was like very, very surprising. So we are not really understand local decodable codes. What true should be. We have some constructions, and that's all. So we don't even know to conjecture where the true lies between these two bounds. So that's why I want to give some framework which matches. Okay, so maybe it's a good idea to give example of Adamar code. Okay, so Adamar code is it's a code of length to the power n. It encodes vector x to all x inner product v for v in f2 to the n. Okay, and now assume that we want to decode some bit xi. So we choose random r, and we query and we note that C of r XOR C of r plus ei is exactly okay. So I need okay. So it's C of x at place r. Okay. XOR C of x at place r plus ei. It's exactly mean x inner product with r XOR x inner product with r plus ei is exactly xi. Okay, so this proves completeness. So if you have uncorrupted code word, then we will get correct answer. And on the other hand, note that if we pick r uniformly from f2 to the n, then this query is uniformly distributed over all the domain, and this query is uniformly distributed over all the domain. So this way we are going to prove today that some code is locally decodable. We'll show that each query is uniformly distributed and that it decodes correctly our code word. Okay, so let me. Okay, I will. Maybe I will erase it. Okay, now let's define. I worry about the length. So this was exponential, but this was this was only an example. So actually, all the question is to construct somehow code which will be the shortest code as possible. And this is really hard. And actually, it's not very hard to construct with constant number of queries. It's very hard to construct something which is sub-exponential. And for 2 queries, for example, it's possible to prove that there is no sub-exponential locally decodable codes. So that Adamart is actually the best possible locally decodable codes with 2 queries. But with 3 queries, you can get slightly sub-exponentially. Okay. So now I want to define what's the representation theory, the stuff related to representation theory. What representation is? Of group G. It's actually group homomorphism. We have rho group homomorphism from G to GLV. What it means? It's what means that it's group homomorphism. It means that rho of G1, G2 equals to rho of G1 times rho of G2. So for each okay, so for each element in group G corresponds some invertible matrix, and we have this property that product of 2 elements in group will gives us product of 2 matrices. Okay, this so representation usually denoted by rho product of V. Now, what's interesting in it's okay. It's just homomorphism of some 2 groups of G and GLV, and why it's interesting to look usually on representation theory is because we can define sub-representation. Okay, so we say that vector space W is sub-representation of V if we have that rho of G of W is subspace for W for every G. So if you have that we have some subspace which is stable under the group action, then we call it sub-representation. And we need the third irreducible representation. What we say that rho V is irreducible if and only if V and 0 are only subspace, only sub-representations. So okay, so here we have some representation. This representation may have some sequence of sub-representation, but sometime we have to stop. So and this will be irreducible sub-representation, and also under some conditions when, for example, we are going to talk today about finite groups. So when say GCD of G, if you have that GCD of size of G and say characteristic of our field is coprime, and assume that our field is algebraically closed or large enough. In this case, we can always decompose our vector space as direct sum of irreducible representations. So in this case, we will have that every matrix of rho of G in some basis could be written in some matrix diagonal form. Okay, so but usually we don't have to assume today that this characteristic is 1, and we may assume that it's not 1, and all the stuff will work. But it's good to know that in this case, in this actually very surprising fact, and it's not, okay, so it's maybe trivial, but very surprising. Okay, so let me give some examples. Okay, so one of the examples, the first example of representation is rho of G is 1 for every G. So it's trivial representation. Note that it's irreducible representation because every one-dimensional representation is irreducible. Okay, this is the first example. Let's consider cyclic group Cm. And let's take gamma, say, in C star. Gamma to the power m is 1. Okay, then we can rho of x to be gamma to the power ix is also one-dimensional irreducible representation of a cyclic group, and it's possible to show that with all irreducible representations of a cyclic group over C. Okay. Next, very important example for us today. Assume that we have some group G and it acts on set X. So we have some set of permutations of set X, and this is our group G. And well, then in this case, we can define permutational representation. And permutational representation f to the power x. And rho of G is just permutational matrix. So what we have here some set X, and our group G is just permutes our coordinates. It's a permutational representation. It's a very important class of representations, and we are going to talk a lot about them. And I want to mention that permutational representation never irreducible. So take vector 1, 1, 1, vector in f to the power x. Then this vector spans one-dimensional subrepresentation of f to the power x. So this permutation is never irreducible. And here examples for subrepresentation. Okay. one more thing it will be convenient for us to define is group algebra. Before I forget. In case when x is equal to g, okay, when f to the power g is called regular representation. Irregular okay. Now I want to define group algebra, and group algebra is just formal. We will have formal sums ci, gi, and we have that say g1 times g2 is just element g1 g2, and we have just multiplication as a convolution between two elements. This group algebra, and it's very convenient for us to define. And what I want, it's denoted, group algebra denoted usually by f of g. And not one notation also. Assume that we have a representation rho mapping from G to GLV. In this case, we can extend this representation to the group algebra just by linearity. So we can define rho of sum of Ci, Gi, just sum of Ci, rho of Gi. And by the properties of the representations, we have that rho of f convolution with G is just rho of f times rho of G. When here is f and G will be the any two elements in group algebra. So in this case, it's equal to multiplication of matrices. And this extension, just we need to mention that this extension from to f of g is not to invertible matrices, but it's to some matrices. And in case when representation rho is irreducible, this mapping is also onto. Okay, so and okay, maybe I want to say okay, so what's the condition for what's condition that we'll use today for reducibility of the representations is the following. We say rho v is irreducible if and only if the following set rho of g small v, say u, g and g, say tu, if this tu spans v, the whole set v Okay, so what we need that if you take any vector in our vector space for any u non-equal to 0, if you have our vector space, we pick any vector, and we act with our group on this vector, then it have to span the whole vector space. Does everybody see why it's true? For every u. What? Yes. Okay. So, for example, assume that we have irreducible representation, and let's pick some u in V, and let's consider on this span of Tu. And what I claim the following: that span of Tu is a sub-representation of V. Span of Tu sub rep of V. Why is it true? Because if you have some vector which is sum of Ci rho of Gi of times u, and we act this here by rho of, say, some h, then this linear, and it's just equal to sum of Ci rho of h rho of Gi u. Is equal to sum of Ci rho of h Gi u, and this is in span of Tu. So this is why if V is irreducible, then we will get that every vector spans the whole space. And in the converse direction, if you have reducible subrepresentation, then we have subset W, and if okay, and we have subset W, and it's definitely that if you take any vector from this subspace subset W, then T of W will be also subset of this. So this in fact equal definition. So it's nice. Okay. Now okay, so now what we will show today, theorem, is the following. Assume that we have some irreducible representation rho and V. Irrep is a irreducible representation. Okay, we have some reducible representation, and we have the following thing. We have that sum of Ci rho of Gi, where I goes from 1 to Q, rank 1 matrix, then exist locally decodable code C from V to f to the power G with Q queries. So if you can construct some sparse element, it's in group algebra, which gives us rank 1 matrix, then we can construct locally decodable code with a number of queries as the sparsity of this element, and its length will be corresponding how large our irreducible representation is. So, for example, this theorem cannot give us better than quadratic locally decodable codes, but even quadratic locally decodable codes are very interesting. And very soon we'll prove some extension of this theorem, which when we also don't know to prove quadratic lower bounds. Okay, so not from exactly this construction, but from some extension of this construction. No. No, cannot. Okay, so what else? What else I want to say is the following: that here we have some d which is sparse, and we have that row of d is rank 1, right? But I want to mention that you always can find some element in group algebra which will give us a rank 1 matrix, because we know that row from f of g to matrices on V is onto. So this mapping is onto, and we always have we always can find the rank 1 matrix. The only catch is how to find it that it will be sparse. So everything is easy. It's easy to find the sparse element in group algebra, and it's easy to find rank 1, but okay, so you will have here some this, but in local decodable codes, not distance is not really important, because you'll have some distance here, because every code must have distance.
No, but I mean, where does your smoothness come in here?
Okay, so let me just here I will show that you can construct that it will be smooth, that you can construct C, which will be actually a morphism of the representations, which I need to define in a moment. Okay, so let's continue and we'll see. So okay, so smoothness here will be like that each query is distributed over all the domain, almost all the domain. What? No, it's dependent Q, because it depends on the code. It depends on Q, because all what I'm talking, I'm not talking today about an error, because okay, I told it in the beginning that all our codes which we are going to construct will be smooth codes. So I will show only that each query is uniformly distributed over a large size of a domain, and that if you get a correct code word, then you will get correct answer. And in these codes, you will have that the probability for error is q times the number of places which are disturbed. So
I guess I don't understand the theorem statement. So where in your hypothesis in this theorem, what part of that affects the smoothness?
okay, each query is here smoothness. Okay, so smoothness you will have if you have delta fraction of errors, then the probability for mistake will be at most q times delta. It will be perfectly smooth. Maybe I'll divide by half, but it's what I will show today, but it's 2. but it will almost move. And okay, so what I need to, okay, I need one more definition from the representation theory, and we are I need definition of morphism. Now, okay, so now what I'm going to do, I'm going to prove some more complicated theorem and more general. And then from this theorem, I'm going to deduce to show that this is a special case. Okay? So one more definition is homomorphism. Morphism of what it is defined homomorphism of representations. Okay, so assume that we have here V, and we have here rho 1 of G, and here we have T. I will just rho 2 of G. Okay, so I will just explain what I have around here. So I will say that a linear map T from V to W is a homomorphism of the representation if the following diagram is commutes for every G. Okay, what does it mean? It means that we have some mapping from T to W, and it means that T of rho 1 of G equals to rho 2 of G times T. It's just product of matrices. Okay, so it means that this mapping T actually, in some sense, commutes with representations for every G. This homomorphism of representations, and maybe it's somehow hard to catch this definition when we begin. So let me just maybe give an example. So I will erase this theorem. And these examples are always comes from group G as Sn. And let's our vector, our rho 1 V be permutational f to the power n, and rho 1 f to the power n. And it will be just a permutational representation on n coordinates. Just element will permute our coordinates according to permutation. Okay, and let's take rho 2 V will be rho and f to the power x, also permutational representation, where x will be subsets of size k. W. Thank you. Okay, so we have all subsets of size k, and you have a group Sn of all permutations acting on this x. So just taking the subset, move each element, and get another subset. Now, what I want to define you T from f to the power n to f to the power x. Okay, and I will define it only on basis, and T C of, say, EI will be sum of ES I in S. Okay, so we have a basis, natural basis here. EI is just elements from 1 to I, and here a natural basis is just indexed by sets of size k. Okay, so we will define it by sending each EI to all to sum of all subsets which contains this I, and it's easy to see that if you have some function f in f to the n, then by definition T of f is just T of f at the place S is just sum of f I in S. And now we need to, okay, so you almost see it from the definition that if you apply permutation here, and after it apply on this mapping T is the same as first applying mapping T, and after it applies permutation, the same permutation here. It's just definition, and this what's mean homomorphism of representations. And okay. Also, maybe I want to mention that if you have a irreducible representation, then either it goes to 0, or it doesn't have a kernel, or it's one-to-one representation, because kernel of this and also image is they both are subset representations of representation. Okay. I will write an example. Okay, so now I want to say like main theorem, most general theorem, which is okay. So assume that we have a representation ρ and V, irreducible, and assume that we have D sparse element, sum of Ci, Gi, I goes from 1 to Q, as before, such that ρ of D rank 1. Now, the second thing that I want to have is C from V to f to the power x homomorphism. What? No, now I'm in any group. X is any. Okay, so now I want X is any X. Assume that you have some X, and you have some homomorphism from your irreducible representation to permutation representation. Yes, G acts on X. G acts. Okay. So C is homomorphism of the representations, and I need third thing is okay. So we have that ρ of D is rank 1 matrix. So rank 1 matrices are it has one element in its image, one vector. So it could be written as U of V times U of X times V. So every rank 1 matrix I can write as some linear functional from acting on X. So if it's rank 1 matrix, then it's some linear functional or action on X times V.
So that's not the same X. That's above or
Above what?
in F to the X.
It's maybe it's double. Say W. No, it's just for every W. So I'm saying that every rank 1 matrix could be written as the tensor product of U tensor V, where U is in dual space and V in your space. So okay, so this is another way to write it. And in this case, what I want that C of V has large support. Okay, so what? Okay, so I need that row of D is rank 1 matrix, and I need to have that C. Okay, so this and I need some homomorphism of the representations. I need that this has large support. Okay, so first I'm going to prove this theorem, and next I'm going to show that. Okay, sorry. When exist basis B1 till Bk for V, such that C of sum of Mi Bi is LDC. Okay, so we are encoding our message M1 to Mk to C of Mi Bi for some basis, and this will be our locally decodable code. No, V is this V. For this particular V, is rank 1 matrix.
V is basically any vector in its image.
Yes, V is any vector in its image, and I want that this vector of the image of row of D has large support. And okay, so somehow we can always construct homomorphism for any reducible representation. I will show later that for any reducible representation and for any vector V, you can always embed it to regular representation in the way that it will have large support or full support.
So V is in the space capital V.
Yes.
And does that have a given basis? I mean, large support means
La
a basis.
Okay, so but f of x has natural basis. It's permutational representation. And I assume that it has natural basis by
Okay, so C of V has large support. Okay, that's in F to the X.
C of v in f to the x, and it has large support.
So the difference between this and the previous theorem was that this condition 3 was not there and x was
Because okay, difference was okay. Yes, so difference was x was all f of g, and somehow it's it seems that it's not very hardly extended. But for example, for matching vector codes, it's possible to show that it's always possible to embed it to some very small permutational representation, but you never can. But for this embedding, you don't know how to make this condition hold. Mean most of COV it's yes. Yes. No, but there is no permutation. It's C of V is just element in. So it and this large support will comes into play how large smoothness you will have. So okay, your code will be from V to F to the X. Okay, and if you have a large V and small X, then you will get good parameters, and you have vice versa. You have bad parameters. Maybe you can make an example. So once again, yes, yes, when you have the whole group G. Okay, actually, okay, so actually you can have X larger than G. You can just take, for example, two disjoint copies of G, and then it acts on each one separately. But in fact, you can just take X to be one of the orbits, and in this case, if G acts on X transitively, then X always smaller than the size of G, and in this case, actually X can be represented as a G divided by some subgroup H. Okay. For I can always find such a V for every case. So I can. What mean I can always find? I can always find the C homomorphism to for every also when characteristic divides. I will show. We can check it together. Yes. Right. Okay. So okay. So let's take an example. I want where it will also will be two query locally decodable codes, and also will be exponential lengths. Okay, so we have G group Sn, and we have f to the power n permutational representation. Now let V be all functions f from n to f, sum of f of I is 0. Then I claim that this V is irreducible subrepresentation. Okay, I will not prove it now, but you just believe me. And next, let's take. Okay, so next I want to construct two elements which will give us rank 1 matrix, and let's consider identity, pahot, matrix which permutes 1 and 2. Okay, so I'm claiming that just permutation of 1 and 2. And now what is this? It's if you are looking at a submatrix of f to the power n, it's identity, and here it's minus this matrix 0, 1, 1, 0, right? And what we'll get here the matrix 1, minus 1, minus 1, 1, and 0. And we see that this rank 1 matrix. And you need to show to check that this indeed goes well through sub-representation, but it's do. Okay, so we have V and we have two elements in V which sum up to rank 1 matrix. So we are fine, and this way, using the basic theorem, you already can construct local decodable codes which sends n minus 1 bits to n factorial bits. It's already fine, but let's take x to be n, choose n over 2. And our C will be as we defined before. Okay, C of f at place S is just sum of f of I in S. To be Sn. Yes, all subsets of size n choose n. And we have defined already homomorphism between this and this guy. So, and by definition, it said that C of f of S is just this sum. And now, what is the image of this matrix D? The image is spanned by the image of this is just spanned by vector, it just span of 1, minus 1, and zeros, right? So I will ask what's the support of C of this image? C of 1, minus 1, and zeros. Okay, so when we apply it on S, if both 1 and 2 are in S, we'll get 0. If they both are not in S, we'll also get 0. And if one in S and another not in S, we'll get 1 and minus 1. So it's all S's support of this is all S's S has exactly 1 between 1 and 2. Okay, so we have approximately half of support will be approximately half, and we instead of getting code of length n factorial, we get code of length almost 2 to the n. So sometimes it's important to take some permutation representation. It may help. What's with English? No.
It's not the Hadamard?
No. No, don't think so. What? Yes, it's two query release. Okay, so here, here you can show that this representation is irreducible for any finite field, and it may be any finite field. And I also want to mention here that our codes has good properties that if you have sub-extension of, say, F2 to the, if you have some finite field, say, if you work over, say, finite field Fp to the N, and say over Fp, and you have some algebraic closure, then you can always reduce your alphabet to Fp. So just you can always think that you're working over algebraic closure because you can always reduce our alphabet. worry about the size of alphabet today.
So also, like, so suppose you were doing all this over F2, when you said, like, so Hadamard is an example of such a code also, right?
Yes.
But that's a very quite different.
I think so. Yes.
There the group should be
Yes, where the group is a group of all affine transformations, and here a group is a group of Sn. But you know, affine transformation contains a group of Sn, so I don't. Okay, so I don't see the connection of this to Hadamard code, but as Zev says, it cannot be too different from Hadamard. So, but it's some other code, so we don't know how it's related. Okay, maybe I will put it here. Decoding function. Okay, so let's see it just now. Okay. It's so okay. So now let us prove a theorem. Okay, so we have a sub-reducible representation, and we have sub-element D, which is of rank 1. Then I want to claim the following lemma, which I will lemma exist basis beyond to be k for V and G1 to GK elements in G such that row of D times GI applied on BI BJ delta I JV. Okay, it's a sub duality theorem. So what I will say is the following: that
What is this a V delta ij times
okay,
V? What is V?
V is before
Oh, that element.
that element, and what I'm saying is okay. So what's important here is the following: that if we can make we can move just our D, multiply, make convolution with GI, just move it somewhere, and such way that D of every element will be 0, on every basis will be 0 except for one element. Okay, so this is what we are going to use, and like just for sanity check, this row of D of GI is 0 on has a kernel of a dimension n minus 1. So it's all these elements are of rank 1. Okay, so maybe before I will leave a proof for later, it's just a definition of a dual representation, and almost that's all. And let's now I will explain how you are going to decode using this lemma. So now we have this element D star GI, and now assume that I want to decode ith bit. I'm looking on this element D times GI, and what I'm saying, I'm saying that I can calculate rho of d times gi applied on element W at place x with q queries. I will explain with q. Okay, so assume that we have okay, so assume that we have W, which is in f to the power x. Okay? Q is number of terms in D. And note that number of terms in D star gi is the same. Okay? So now assume that, okay, so rho is for, let's say tau. Tau, it will be our permutational representation of on f to the power x. Okay? So what I claim that I can calculate, I can take any element in f to the power x, and I calculate this guy at any place with only q queries. No, it's locally decodable code. No, don't try to correct it. Right, try. Yes, but I still don't know how to correct with these things. So, but I'm almost sure that they will not be locally correctable. No, I'm not trying. I'm just saying that I can calculate this with q queries. With only what I'm saying. And why it's true? Because, okay, I can calculate tau of g on W at place x with one query. Why it's true? Because what's mean tau of g on W? It's actually mean that take W and permute its coordinates. And calculating x, just take the coordinates corresponding to this permutation. And that's all. And now what's this mean? It's just I'm adding up q elements in these things, and I can do it with only q queries. Okay? So I'm fine. And actually what I want to say is that this almost equivalent that I can calculate tau of g on W with one query, it's almost equivalent to be permutational representation. It's some generalization of this you needed. It's actually monomial representations. And actually, we can do all these theorems with monomial representations, but in order to keep things simple, I prefer to work with permutational representations. But it's possible to extend it to monomial representations also. Okay, so this is the only place. Okay, so what's happened now? Now we have, okay, so what will be our code? Our code will be C of sum of mi bi. Now what I can do, I can calculate here tau of tau of d star gi. Okay, I can calculate it at any place R. But recall that we said that our code C is a morphism. Okay, so I can put it here. It will be C and here will be rho. And now use the lemma. So the lemma tells us that all the guys except maybe here summation on J. All the guys except the ith guy will die. But rho of d times gi will kill everyone except the ith one. So what we'll get? We'll get here C of rho of d star gi times bi, and here we'll get mi, because mi will go out because it's everything is linear here. And this guy we know. Okay, so we know I, we know bi, so we know to calculate this guy. Actually, what it's equal to mi c of v. And this we know that we can calculate it in every r. So as long as c of v at place r is non-zero, we can get mi. Just divide it by this, and you are done. So you have very, very simple decoding algorithm, and you just take several permutations of your code, add them up, and you just have your code. You have code word. We just permute this some one permutation. Say 3 permutations. We add them up, and we get mi times something what we know. And this why we are fine. So this decoding algorithm, and it will be smooth because we said that support of v is large, and in case that support of v is large, we will just pick r to be random element from the support of v, support of c of v, and just see that if you have r random element from large support, then each query will be each query will be the form g times r for some constant g, and this also has uniform distribute over some large support. So this is a decoding algorithm, and actually it's based on a very, very simple observation that if you have a permutation representation, then you can calculate tau of g on w at any place with only one query. It just okay, so it looks very simple. Large support because we choose r from this support, because if c of v at place r is 0, we still don't know how to extract mi from this. No, it's not perfectly smooth. It's smooth as the size of the support. Yes, because if you pick r at random, then each query, okay, so what queries do you have? You have queries of form g times r, where g's are elements from this one. And if you pick something, some large r at random, then this also will be distributed uniformly and randomly over large support. So no, but GI are some no. Okay, you maybe. Okay. So what I have to show is only the lemma, right? So let me explain how the lemma goes. Okay, to show the lemma, we need to define dual basis. Okay, so what's dual representation? Okay. Assume that we have some representation v and rho. Then we can define v star and say rho star dual representation by the following. V star is all the linear functions from v to f. Okay, v star linear functionals on v. Okay, and how we define? Assume that you have some L linear functional in v star, then rho star of g on L, say applied on element W. What? Rho star of G applied on L. This, and so you have some element L in V star. We apply rho star of G on L, and it's how I define it by just defining what's linear functional it will get, and it will be L of rho of G minus 1 applied on W. For example, if you have a group CM, cyclic group, and you have a representation rho of x equals to gamma to the power x, then its rho star representation will be of x gamma to the power minus x. Okay, but you make transpose and make inverse. Or inverse and transpose, I don't know what. Yeah, okay, so you're right. You need to check that this will be indeed representation. So rho star of product will be, but this is why I need this minus 1. Else it will not happen. Though it's always confusing when you have to write minus 1 plus 1. But okay, but this is what we have. Now, let's, okay, so what I claim the following thing is if we have that V and rho irreducible representation, then V star and rho star is also reducible representation. It's if and only if. And okay, so maybe I'll not prove it, but it's almost the same as the lemma. We proved it, but these two representations are reducible if and only if. Okay, but now what I'm going to show. Okay, so let's take U to be this U in V star. Okay. Now V star is the irreducible representation. This means that this group, this rho of G U span V star. Note that here is the only place where we're using irreducibility. And we will not use it anymore. So, and this implies that exists G1 up to GK such that rho of GI U is a basis for right. Okay, so I will not change indices anyway, but you're right, it's not the same. Because it's okay. It's the basis for V star. And now take your BIs to be let BI be dual basis. And okay, so up to -1, I think we are done. So this GIs will be this GIs of the lemma, and this GIs will be a basis. Why is it? Because we know that. Okay, so what I claim the following, that we need to check what is it. Rho star of GI U is, I claim that it's in fact equal to, okay, rho star of GI U on of X times V is it's in fact equal to rho of D GI -1 X. Okay, sorry for too many. Okay. And this actually falls from the definition. You need just to take brackets, but actually what, okay, so it's actually just the dual basis. So you check that, okay, so what does this mean? What's mean rho of rho star of GI on U applied on X? It's just mean that it's U on rho of G -1 applied on X. And what does this mean applied on X? It's also the same. It's rho of D times rho of GI -1 applied on X. So just take these brackets and note that rho of D is just U tensor V. So this where we are, and we have okay. So now we have proved the lemma, and we have almost everything, right? Yes, and it's a good question, because probably I want to talk about it now. What? Yes, I think I will. So what happened? Okay, so what I want to say is the following. In general, we used only here the fact that it's irreducible, but we have a theory that it's irreducible if and only if we have all for every V it's spans. But it also may happen that, for example, for some specific U, this still spans V star, but the representation is irreducible. But representation is reducible. Okay, so actually this, I want to say that this cannot happen in case when irreducibility is essential when we are talking about semi-simple case. So if we are talking about, if we are talking about semi-simple case, then this irreducibility is essential, and I will explain why. Okay, so okay, so assume that we have some rho and v, say reducible representation. And now, what does it mean? It means that it can be written in this form, as every element rho of G can be written as form of two diagonal matrices. And in this case, what will be, if you are looking at Ci, Gi, you are looking at rho of this, it will be just, it will be, on the one hand, it will be rank 1 matrix. On the other hand, it will be matrix of this matrix diagonal form. And in case that it rank 1 matrix, it means that one of these matrices should be 0. Here should be 0, here we have 1. It's 0 elsewhere. So what we'll get here in this case is that V is lies in V, and also U star lies in some sub-representation. And you can just reduce ourselves to this sub-representation. But what I want to say is that it's interesting to, this question becomes very interesting in case when GCD is not 1. And it's also maybe one of the directions I think it's very interesting to go is to develop this theory when GCD of the size of a group and the characteristic of a field is not 1. And the main reason why it's very interesting, because in this case there is such thing called radical of a group algebra, which we are the, okay, there is a well understanding, maybe I'm not well understand, but it's well understood, and usually elements from the radical sends elements from the representations to have also small rank. So there is a lot of things to do there, but it's maybe one of the future research directions which are very looks very promising. But so, and also yes, okay. So and also in case of Reed-Muller code, it's also an example of reducible representation, where we have that it's reducible, but we still have this property that rho of GU spans the whole space, and this why it's maybe very very interesting. So okay, so and it's possible. Okay. Yes. So okay. So this only place where I used that it's reducible, and if you have rho GU spans V star, then everything also holds, and even you can take even less hard restriction. It's enough for you that rho of GU has a large dimension. If in case that it has large dimension, you can just also take a basis for this subspace, and you can take its dual basis, and everything will work. And what I'm saying is that in case when characteristic does not divide the size of a group, it doesn't help you. So you have to work with reducible representations. But in case that it does not, many different interesting things are happen, and it's maybe very very exciting and interesting to study this. Because, for example, Reed-Solomon codes, Reed-Muller codes are examples of reducible representations, because Reed-Muller codes are in fact codes which are all polynomials of degree at most d. And say polynomials of degree d minus 1 are sub-representation of Reed-Muller code. And you know that its Reed-Muller code is locally decodable, and you can just check that it's meets this framework. So maybe it's not very easy, but it's technical. And And it looks like something with very natural and something that comes very naturally. And
Are there locally decodable codes that don't fit into this framework?
I don't know. So I don't know about any locally decodable codes which don't fit this framework. But as I okay, so
So matching vector codes do fit in this framework?
okay, I have they do. Probably will
Probably
discuss.
not directly though, right? But
They do, but not for every matching vectors.
okay. So the way in which the matching vectors are sometimes generated does in fact fit in some cases, but not always.
So you can okay. So what I'm saying is following. You can construct matching vectors where matching vector codes which will not fit in this framework, but we don't know to construct good matching vector codes which will not fit in this framework. So all sub-exponential. So we don't know to construct sub-exponential matching vector codes which does not fall in this framework. Okay, so what I can to do now? Okay, so I can we have two options, or I can to explain how how matching vector codes related to this framework, or I can to explain how you can how you can embed your code into group algebra. So the second thing is more intuitive and less technical. So what do you prefer? Okay, so let's. Okay, so now assume that you have V and rho rep, and you have some element V and V. And what I want to say is the following: that there is always exist C of V, say, with full support. Okay. And okay, so C, where C is from V to f to the power g. Okay, so how we are going to show this? First of all, I want to understand how can we construct all embeddings from irreducible representations to group algebra, to regular representation. Okay, so the easy thing is to construct all the representations from f to the power g to v. And why it's easy? Because once you can map 1 to anywhere in V, and once you map 1 anywhere, then G is just mapped, have to be mapped to rho of GV. And therefore, this defines the mapping on 1, and this gives us the full for any vector V. I just can construct this embedding onto V, and all possible CVs are CV of F is just sum of, if you have F CV of, say, sum of CI GI is just will be sum of CI rho of GIV. Okay, so this all it's easy to show that with all the mappings from f of g to v. In order to go other direction, it's a little bit tricky, and what we need to take a dual. So once we take a dual, we will get all the mappings from V star to f of g star, and this is equal to f of g. And what are all the mapping? We have that for any u, say in v star, we have that c u of v is just sum of u of g minus 1 v g. It's just do this trick, and it's need to be checked with indeed what you get. But this all the embeddings that we'll get. But now note that u is maybe any linear functional. So once you have your field size is large enough, you can check you can just pick with all non-zero vectors. So you can just pick such u which will be non-zero on every vector. So and therefore maybe any linear functional and pick u such that u of gv is non-zero for every v. And it's always possible when you have a large enough field. And also this, okay, so maybe what's interesting with proof that it makes you guess when it's possible to embed to permutation representation. And when it's possible to embed to permutation representation is when you can pick u which fixed by a large subgroup. In case where you can pick u such that hu is equal to u, okay, in this case you can also embed not only to f to the power g, but you can also embed it to you can also embed, in this case you can also construct f from v to f to the power g divided by h. So this why maybe I wanted to show this, because it gives you somehow which u's you want to pick or how you want to pick them. And so you want to pick some u which fixes. So if it was like random u which fixes such h, it will be wonderful. But somehow in groups nothing is really random, and everything is very, very structured. So this is what's happened. Okay, now we have 10 minutes to explain about matching vector codes. Okay, so what matching vector codes are?